Hey kids, welcome to section 7.4 confidence intervals for variance and standard deviation. Today we're going to learn how to find confidence interval for a variance and for a standard deviation. So in statistics, the variance and the standard deviation of a variable are just as important as the mean. Remember, the mean is going to describe for you what the average value in the data set is, but the variance and the standard deviation are going to tell you how spread apart the data is in the list. So to calculate these confidence intervals, a new statistical distribution is needed. It's called the chi-square distribution. Now, the chi-square variable is similar to the t variable in that its distribution is a family of curves based on the number of degrees of freedom. So take a look at this graphic here. We have first degree of freedom of 1. Notice it's got a very high peak and it's right skewed. Well, let's bump up the degree of freedom to 4, which means a sample size of 5. And now we're at this blue graph. And now we've scooted over to the right a little bit. We're a little less skewed. Then we bump our sample size up to 10. We're this orange graph here. And then we bump our sample size up to 16, and we're this gray graph here. And as you notice, every time we bump the sample size up, the graph shrinks vertically. And as it does, it gets closer and closer to the normal distribution. So something to think about, that the chi-square distribution may eventually become normal. Okay, the symbol for chi-square is this fancy looking X with a 2 here. So it's a Greek letter chi. It's pronounced chi, obviously. To draw it, you draw like a fancy little X and then a regular part, and then you put your square. A chi-square variable can never be negative, and the distributions are skewed to the right. So we already talked about how the distributions are skewed to the right, and here is a chi-square table. This is a chi-square table that has alpha at the top and degrees of freedom down the side. Now, it doesn't say anything about confidence level, but it is a symmetric table. So there is kind of this middle where it goes down the table and separates the data into a right side and a left side. The values on the right side are chi-squared rights, and the values on the left side are chi-squared left. Now, if you notice, the values on the right half are always bigger, almost significantly bigger than the values on the left side. Also, notice that there's no confidence level at the top. Well, if we scroll down to the bottom and look at the bottom of the page, it tells us that our alpha is the area only on one side. That's because each chi-square distribution is right skewed, so all of the alpha area is not split on the right and left sides like it has been so far, but is all concentrated on one side. Therefore, when we look and try to use this table, it can be confusing because one would think that point 10 would go with 90%. But because the area has to be divided into two sides to make a confidence interval, this 0.05 goes with 90%. And then the next one is 95%. And then 98%. And then 99%. Now, each confidence level is going to have two critical values. The other critical values are on the left side. They go out. So 90% goes with 0.95, then 95%, then 98%, and then 99%. Okay, so notice all the values within the table are all positive. The smallest value is 0.001, and the largest value down here is 140.169. So I'll teach you how to use this chart in a little bit. If we look back, the next bullet says that at about 100 degrees of freedom, the chi-square distribution becomes somewhat symmetric. So once we get to a degree of freedom of 99, because that's what 100 is, then we're going to have a much closer picture to a normal distribution. And last thing, if the number for the degrees of freedom is not given in the table, use the closest lower value. So that means if I look at my table and let's see what's the highest degree of freedom. Okay, so if I said a degree of freedom of 54, 54 would round down to 50. If I said a degree of 59, that would still round down to 50. So whether it's 54 or 59, you would always round down. That way you're not over exaggerating or over inflating the chi-square value that you need. All right, so here are characteristics of the chi-square distribution. There are 4. Number 1, all chi-square values are greater than or equal to 0. We already talked about that. If you look in the table, all the values are positive. Number 2, the chi-square distribution is a family of curves based on the degrees of freedom. We talked about that in the previous slide, how as your degree of freedom increases till it gets close to 100, your graph is going to become less right skewed and more symmetric. Number 3, the area under each chi-square distribution curve is equal to 1. That's true of any probability distribution, that the area underneath the curve equals 1. And then finally, number 4, the chi-square distributions are positively skewed. That means you're going to have a longer tail on the right. Here's a picture of where your alpha now has been split into 2. That's why we had to move over a column in the table. There are 2 assumptions for finding a confidence interval for a variance or standard deviation. Number 1, and this is true of almost every interval, well, this is true of every interval we've written, is that the sample must be a random sample. There cannot be any bias, any kind of skewing of the data in any kind of way. It must be random. And then number 2, this one pops up as well each and every time, that the population must be normally distributed. If the population is not normally distributed, then it's probably skewed in some kind of way, which means there's some bias, which means that it's not a good sample. All right, here are the formulas for the confidence interval for variance and standard deviation. Don't freak out too much. The only difference between the one for variance and the one for standard deviation is that standard deviation has square roots in it. Also notice that the top sides of each fraction are the exact same. The sample size -1 and -1, standard deviation squared, S squared, is the same on the top of both of them. Notice then on the bottom, the chi-square right value is on the left and the chi-square left value is on the right. That's because when you divide, if the tops are going to be the same, then the bottom number has to be bigger if you want the whole answer to be smaller. That's a mind bender. Notice your degree of freedom is n-1. At some point this year, kids, the degree of freedom will be different than n-1. So that is why we keep saying it over and over again. Then remember that if you square root the standard or the variance, that you're going to get standard deviation. So that's why if I take my answers for variance and square root them, I get standard deviation. The rounding rule is the same for confidence intervals in this section as previous. When you are computing a confidence interval for a population, standard deviation, or variance by using raw data, round off to one more decimal place than the number of decimal places in the original data. So that means you have a string of numbers that you're putting into your stat edit so that you can run the one var stat. The second rounding rule, when you are computing a confidence interval for a population variance or standard deviation, and you're using a sample variance or standard deviation, then you round off to the same number of decimal places as that given sample variance or standard deviation. So same rounding rules as section 7.1.2, section 7.1 and section 7.2. All right, here let's do some examples. So find the 95% confidence interval for the variance and standard deviation of the nicotine content of cigarettes manufactured if a random sample of 20 cigarettes has a standard deviation of 1.6 milligrams. Assume the variable is normally distributed. So the formula for finding the confidence intervals requires an n, requires a degree of freedom, requires an s, and also requires a chi-squared right and a chi-square left. So from our problem, our sample size is 20, which means our degree of freedom is 19. If I look in the problem, I also see that I have a sample standard deviation of 1.6. Now, in order to get the chi-square right and left values, I need to grab the 95% from the problem and my degree of freedom of 19. So I'm going to find degree of freedom of 19 and 95%. All right, so if we make this just a tiny bit smaller. There we go. So here we have degree of freedom of 19, and I'm looking for 95%. So I got 95% here. That's 8.907. And then I got 95% here. That's 32.852. So I say my chi-square right is 32.852. And my chi-square left was 8.907. All right, I think we're ready to start our calculations. Remember, the formula is n minus 1 times the standard deviation squared over chi-square right is less than the variance square, less than sigma squared is less than n minus 1 times s squared over chi-square left. So I plug in and I get 20 minus 1 over 1.6 squared divided by 32.852 is less than sigma squared is less than 20 minus 1 times 1.6 squared over 8.907. If I go ahead and plug this into my calculator, the left-hand side is 1.5 and the right-hand side is 5.5. Remember, since we're plugging in values, or we're just plugging in what the standard deviation is, we're not actually plugging in individual data values. I round to the same number of decimal places as the standard deviation, which is 1. Now, this is my variance. Remember, variance is sigma squared. So this is my variance confidence interval. I also need to calculate the standard deviation. So that just involves square rooting. So I'm going to square root everything. And then when I go to calculate what my square root is, try to use the long decimal that's on your calculator and square root that. Don't use just 1.5 because remember you rounded that 1.5. So when you square root 1.5, you get 1.2 is less than sigma is less than 2.3. So this confidence interval here is for standard deviation. All right, so this confidence interval means that we are 95% confident that the true standard deviation for the nicotine content is between 1.2 and 2.3. All right, so our confidence interval says that we are 95% confident that the true standard deviation for the nicotine content manufactured in cigarettes is between 1.2 and 2.3. I guess we could say milligrams just to label our values. Okay, so that doesn't seem like it's a very big standard deviation. It's only 1.1 milligrams in width. Which may not seem like a lot, but it could be a lot when you look at the different levels of nicotine. I don't know. I don't know anything about nicotine, but the other thing that you would want to know is what the mean is so that you could see if comparatively your standard deviation is too big or too small or just right. All right, let's go on to the next example. Find the 90% confidence interval for the variance and standard deviation for the number of named storms per year in the Atlantic Basin. A random sample of 10 years has been used. Assume the distribution is approximately normal. All right, so they give us a bunch of data this time. That means that we're going to have to put this into our calculator using stat edit. So I need to go to my calculator and I need to type in the different values. If I type in the different values, I get a standard deviation of 4.1. So on your calculator, it'll say SX. That's your standard deviation. I also need to know what my N is, what my degrees of freedom are, what my chi-square right and my chi-square left values are. So I did get my 4.1 on the calculator, just so everyone remembers. All right, so my N value is 10, which means my degree of freedom is 9. All right, so we're using 90% and 9. All right, so let's see. 90% and 9. So here's 9. 90% is going to be 3.325 and 16.919. So my chi-square right is 16.919 and my chi-square left is 3.323. All right, so my formula is n minus 1 times the standard deviation squared over chi squared right is less than sigma squared is less than n minus 1 times standard deviation squared over chi squared left. All right, so we have the quantity 10 minus 1 times 4.1 squared over 16.919 is less than sigma squared is less than 10 minus 1 times 4.1 squared over 3.323. All right, so I'm going to find what my variance is, and then I'm going to square root it so I can find my standard deviation. All right, so if I plug all of these values into my calculator, I'm going to get 8.9 is less than sigma squared is less than 45.5. The reason why I went to 1 decimal is because the data that I put into my calculator had 0 decimals. Now if I square root these values, I'm going to get 3.0 and 6.7. So the top one is my variance, and the bottom one is my standard deviation. All right, so there's my answers. And we can say our sentence, we are 90% confident. That's not very confident. That the true standard deviation for the number of storms is between 3.0 and 6.7 storms. All right. Ooh, application problem. All right. So shown are the ages in years of the presidents at the times of their deaths. And all of the data that's here. Notice that it goes from highest is 93 and the lowest is 46. Is that the lowest? Yeah, 46. Do the data represent a population or a sample? And since this is a list of all the dead presidents, this is a population. This is a population because it contains a population because it contains all deceased presidents. All deceased presidents. And I guess we need to say that at the time of this video was being made, this is all the deceased presidents. Okay, then the next question says to select a random sample of 12 ages and find their standard deviation and variance. Okay, so you pick any 12 numbers. I'm going to pick my 12 numbers. I'm going to pick these 12 right here. You can pick whatever 12 you want to pick. Those are my 12. So circle your 12 and find the variance and standard deviation. So that means go into your calculator and put your data in and find your standard deviation and variance. So for my data, I got a variance and a standard deviation. Now, here's the trick, kids. The variance is not on the calculator. You need to find the standard deviation first, and then you need to square it to find the variance. Remember, the standard deviation is SX, not sigma. Okay, so if I put my data into my calculator and run my one var stat, then my sigma is going to be 11.5 years. If I now find my variance, I'm going to square my 11.5 years, and I get 132.25 years. Now you are going to get different numbers because you are picking different numbers. So your variance and standard deviation are going to be slightly different. Hopefully it's not a ginormous difference. Otherwise you might have punched a number in wrong. All right, number 3 says to find the 95% confidence interval of the standard deviation. So that means using your data, we need to find the confidence interval. So I'm going to show you how to do it using my data. So for my data, I'm going to say that my N is 12, which means my degrees of freedom are 11. I can also say that my standard deviation is 11.5. Then I need my chi-square right and my chi-square left. So I need to look on my table for 95% and 11. So let's get these old ones out of here. 95% and 11. And 11. So 95%, we're talking here and we're talking here. So we should have the same chi-squares. That's no different person to person. So the chi-square right was 21.920 and the chi-square left is 3.816. So now I can find the confidence interval for my data by doing n minus 1 s squared over chi-square right is less than sigma squared is less than n minus 1 s squared over chi-square left. It's always good to repeat the formula so you can learn them. All right, so I'm going to have 12 minus 1 times 11.5 squared over 21.920 is less than sigma squared is less than 12 minus 1 times 11.5 squared over 3.816. So if I do the calculations, this gives me 66.4 is less than sigma squared is less than 381.2. Notice I went one decimal. That's because my data had no decimals. And then if I square root, I'm going to get 8.1 is less than sigma is less than 19.5. So here's my standard deviation confidence interval. All right, so keep going with this problem. Number 4, find the standard deviation for all the data values. So kids, if you take all these data values and put it into stat edit and then find the standard deviation, your standard deviation should be 12.0. So now take a look at this, guys. Does the confidence interval that you calculated in question number 3 contain the standard deviation? So find your confidence interval. That's, for me, 8.1 to 19.5. And the answer is yes, because my whole entire population standard deviation is 12. And I estimated that it was going to be between 8.1 and 19.5. So yes, S equals 12.0 is within my interval. Isn't that cool? Hopefully all of you also have the same. Okay, if not, give a reason why. Okay, we don't have to do that. So what assumptions must be considered for constructing the confidence interval in step 3? Well, the assumptions were that it has to be a simple random sample and then it has to be a normally distributed population. So the two assumptions are a random sample. I spelled that wrong. I can't even spell. A random sample. And the second one is that it must be from a normally distributed population. Normally distributed population. Well, I can graph the data values to see if I get a histogram that looks symmetric. And in fact, you do. All right, kids, that is the end of section 7.4. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.